Hello and welcome to our next set of algebra notes. We are on Unit 3, our first outcome. In this section, we're going to introduce the idea of a specific type of functions. We've talked about functions before, but now we're looking at specifically one-to-one functions. And then by having functions that are one-to-one, we'll talk about inverse functions. So first off, we want to get into the idea of what is a one-to-one function. Here's kind of your rule definition for a one-to-one function. A function is one-to-one if different inputs have different outputs. So the math way of saying this is that if two numbers are not equal, then the function value that you get for those two numbers can't match. So different inputs have to have different outputs. You can't get the same result from plugging two different numbers in. That's the important thing that makes a function one-to-one, not just a function. So some functions, we've seen like the constant function before, can give you the same output no matter what input you put in. A one-to-one function follows a rule that every different output has a different input has different output. So these first two show kind of graphical picture ways of thinking about functions. So you can see the x inputs, you can see the y outputs for each of these. And you can hopefully see why the first one is not a function. So this one is not a one-to-one function. So it's not one-to-one. Because 3 and 4 are different numbers, but they have the same 8 outputs. So two different inputs have the same output. And that's what makes it not a one-to-one function. Anytime two different inputs have one result, is the same for both. Versus this one over here, this one, yes, it is one-to-one. You can see that every input has only one arrow going to each output, and they're all unique. So you can see 4 is the only number that goes to 7. 5 is the only number that goes to 2. 8 is the only number that goes to 5. So each one of these results only has one number going to it, versus over here, it had two different numbers going to it. That's what makes it not one-to-one. We talked about before how you can list functions by listing ordered pairs. So let's go through these and see if we can figure out which ones are one-to-one, which ones are not. So this first one, 5, 0, and -3 are all different outputs for these different inputs. So yes, this one is one-to-one. The second one, excuse me. The second one here, we can see that there are two different numbers, both 0 and 2, that give us -3. Because we have two different inputs giving us the same output, this one is not one-to-one. In fact, that's not the only reason it's not one-to-one. It's actually also not one-to-one because there are two different values that are giving us 0. So you can see you can get 0 two different ways. So this actually fails two different times. It doesn't matter how many times it fails. If you can just find one pair of numbers, that give you the same output, but they're different numbers, you can do that. You can find that one time, that's not a one-to-one function. Every different input has to give a different output for it to be a function. Next one here, so 0, -3, -4, and 5. See, those are all different numbers. So all these different inputs, 3, 0, 2, and 4, they all give you different outputs. So yes, this one is one-to-one. Last one here, again, the 5s would be a problem here because we have both -2 and 4 giving us 5. So these would be a problem because then that means it's not one-to-one. You have two different numbers, both -2 and 4. They're giving you the same result, but they're different numbers, and that's what makes it not a function. And the rest are fine. 0, -3, -4 are all different, but that 5, matching 5, that's enough because these two different inputs are having the same output. Now, every function has an inverse relation. So you can always take a function, you can make an inverse. An inverse is just basically doing the function backwards. So every output becomes an input, and every input becomes an output. So, instead of, -2 going to 5, we'd have 5 goes to -2, and that would be the part of the inverse. It's just go backwards. So basically, it'd be like taking these bubbles and switching sides. So this would become your input, and this would become your output. So every function, you can make it into an inverse, but if you want the inverse to also be a function, you have to work with a one-to-one function. So only one-to-one functions have inverse functions. So up here, if you think about this, if I tried to turn this around and go the other direction, so instead of going from the left to the right, what if I go from the right to the left? That's the inverse way. Well, then 8 would give you two different values. It would give you both 3 and 4, which is why the inverse of this would not be a function, because 8 would have two different results. Remember, we said the rule about functions is every input can only have one output, one answer. So if I'm going backwards and turning these into my inputs instead of my outputs, and 8's my input and it gives me both 3 and 4, that's not a function. So things that are not one-to-one like this, their inverses are not functions. But this one over here that is one-to-one, its inverse is also a function. So if I turn this around and go backwards, well, 7 only gives me 4, so that works. 2 only gives me 5, that works. And 5 only gives me 8. So every one of those gives me only one answer, one output. So this would be a function if you just flip it around and go the other way, if you use its inverse. So one-to-one functions have inverses. So that's what we really look for when we're working with functions and we want functions that have inverses. We look for them to be one-to-one. And because these are so closely connected, you'll see me a lot of times talk about something having an inverse function or being one-to-one and kind of using those interchangeably, because if it's one-to-one, it has the inverse function. And if it has an inverse function, it has to be a one-to-one function. So those are important. That's the important thing to know. Well, let's go through a couple functions just to identify that. But before I do, I want to give the proper definition. So inverse functions, we say two functions f and g are inverses if you compose them, if you do both of them. Remember that composition where we do like f of g of x or g of f of x? Well, if you compose them like that and they give you plain old x. Now what's that actually mean? That means that if you put both functions together, remember the composition, you're basically doing both functions, that because one function goes one way and the other one is the opposite, going back the other way, you always get out what you put in. So let's fix that. So if you plug in x and do both g and f, you do both functions, you'll get out x. So inverse functions are inverses. Inverse functions are opposites. They are functions that undo one another. So that's what this means. This means that inverse functions will cancel each other out. They're opposites. If you do both functions in either order, you get back out what you put in. Your result is what you put in. So we call the g function, we call it f inverse. That's what this is. F inverse is the name for that. F inverse. It is the inverse function of f. It's the opposite function of f. It does the exact opposite. Important thing to note about these inverse functions, the inverse functions, f and f inverse, is that the domain of f is the range of f inverse. Remember, the domain is the x values and the range is the y values. So f starts at the x values and gives you the y results. So the inverse function has the opposite domain and range. So the domain of f is a range of f inverse. The range of f is the domain of f inverse. Basically, you're switching the x and y's. The x's of the f function are the y's of the inverse. The y's of the f function are the x's of the inverse. So basically, switching x and y will get its inverse. That's an important thing to know. We'll see that, when you're looking for inverse functions, that's the big trick, is to switch the x and the y, because the inverse function works opposite. It goes exactly backwards. And so you can literally switch the domain and range values. You can switch the x's and the y's. Okay, so here they give us functions. We don't know if there's one-to-one or not. So we're going to find the inverses, and then we're going to just state whether the inverse is also a function. So I have this function. I want to find the inverse. To make the inverse function, what I'm going to do is I'm going to just switch all these x's and y's. The inverse function, instead of going from 3 to 5, it's going to go from 5 to 3. I'm going to literally switch the x and y. Instead of going from 7 to -2, it's going to go from -2 to 7. Instead of going from -4 to 6, it's going to go from 6 to -4. And instead of going from -1 to 5, it's going to go from 5 to -1. So by switching the order, from switching the x and the y's, we get the inverse function, and this is the inverse. We do have to be careful to make sure this is a function. Now we knew that if this was one-to-one, this would be a function. And if you look at this, you notice that it's not one-to-one, right? You can see that both 3 and -1 give you 5. You can see here that both 5 and 5 these have two different results for 5. So no, this was not 1-to-1. So it wasn't 1-to-1 to start with. So the inverse is not a function. We didn't even actually have to find the inverse to figure out if it was a function. We did, because we needed to find the inverse anyways. But we could have looked at the original function and said, that's not 1-to-1, so this won't be an inverse function. It's an inverse, but it's not an inverse function, because 5 has two different results. Remember, you're not a function if one input has two different results. Let's try the next one. Make the inverse of this function. Again, this is a function. We're going to make its inverse. We need to figure out, after we make the inverse, we're going to figure out if it actually is a inverse function. Again, to make the inverse, we switch x and y. So 12/25 becomes 25/12. So instead of going from 12 to 25, it's going backwards from 25 back to 12. 14/28 becomes 28/14. 11/22 becomes 22/11. 17/31 becomes 31/17. 9/17 becomes 17/9. Okay, now again, we look here and we look for anything that's repeated. 25 goes to 12, 28 goes to 14, 22 goes to 11, 31 goes to 17, 17 goes to 9. Nothing gets repeated. 25, 28, 22, 31, 17. There's no repeats. Here you'll notice that we never had the same output because all the inputs were different. So this was a function, a 1-to-1 function, and this is a inverse function. So inverse function, it's because, yes, it's a 1-to-1 to start with. If it's 1-to-1 to start with, then the inverse is going to be a function. So the inverse is a function. Of course, in real algebra, in most of the class, we're not going to work with sets of ordered pairs or those pictures or graphs we're dealing with. Most of the time we'll deal with equations. So most of the time we'll have equations like this, and we'll be trying to decide if they are inverse functions, if they're 1-to-1 and inverse and all that. Now the easy way to tell if two functions are inverses is they should be literally opposite. And you can check that by composing them, by putting them together. So we're going to check to see that both f of g of x is x and g of f of x is x. So if you compose them both directions, you should get just plain old x. They should cancel out. Now, one thing you kind of look at, and this is going to be pretty true, things that are opposite operations are going to be opposite functions. Like adding 2 and subtracting 2. Those are opposites, right? Opposite of adding 2 and subtracting 2. That would be opposites. In this case, you can notice that this function takes every x and multiplies it by 4, and this function takes every x and divides it by 4. And multiplying by 4 and dividing by 4 are opposites. So I can tell you now, before we even do the problem, that we're going to expect these to be inverse functions, because they are literally the opposites of each other. So as long as inverses exist here, because these are 1-to-1 functions, which they are, you can have them be, they will be opposites, they'll be inverses. That's what we'll see when we'll do these compositions. So let's do first up, we'll do f of g of x. Means we're doing the g of x first, we're plugging that inside, so we're going to take f of g of x, which is x over 4. The f function just takes that and multiplies 4 times that, so we're going to do 4 times x over 4. But here we're taking this amount, we're dividing by 4, and we're multiplying by 4, and so those 4's cancel, right? Multiplying by 4 and dividing by 4, those are opposites, so this becomes just plain x, and it actually checks out that way. So this direction, it works fine. That is inverse functions. And we kind of expected that, so we're not a big surprise. Now we're going to go the other direction, because it has to work both ways. So we're going to do g of f of x. Well, f of x is just this, x to 4x, so we're going to do g of 4x. That's what f of x is. It's 4x. And then g takes whatever and divides it by 4. So we're going to take that 4x and divide it by 4. So we're replacing that x with this 4x, we get 4x over 4. Now, 4x over 4, got multiplication on the top, division on the bottom, those 4's do cancel. So this also just gives us plain old x. And that's what we're looking for, right? We're looking for everything to cancel, so you're just left with an x by itself, because that means the input, the number you put in, x, is the same as the output, the result you got out, x. Because the output matches the input, both directions, we can say yes. F and G are inverses. In fact, now, to make it clear to everybody, instead of calling it g anymore, we'll typically start calling g f inverse of x. So that's the way we label it and say, this is the opposite function. This is the inverse function. And you could go the other way. You could call the f function g inverse, and that works fine. It doesn't really matter which one you call g, the function, which one you call the inverse. But they are opposite functions. We usually like to work with f, so we usually call that one f and that one f inverse. That's just kind of typical. That's the idea. We checked it because we did the composition. If you compose it both ways, and both ways you get a plain old x, then you can say, yes, those functions are inverse functions. Okay, let's try another one. We want to figure out if these two functions, if they're inverse functions. Now, the last one, it was pretty obvious because you could see that multiplying by 4, divided by 4 are opposites. Here it looks like it's potentially going to work out because we have multiplication, subtraction. Here we have division and addition. So I'm kind of thinking, hey, maybe this will work out. Maybe it'll be inverses. But to figure it out for sure, we got to compose them again. So we're going to start. It doesn't matter which one you start with. So let's go ahead and just start with the f composed with g. Do that one first. And again, it has to work both directions. So if it fails one direction, it doesn't work. They're not inverses. But we got to check both directions. So g is this whole x plus 5 over 9. So we're going to do f of x plus 5 over 9. The whole thing. That means we're taking this 5x minus 9, we're replacing the x with all that stuff. So we're going to get 5 times x plus 5 over 9. Sorry, that's supposed to be an x minus 9. Now, right now it doesn't look like plain x, but one thing you have to be careful about is you always should start off by trying to simplify it a little bit if you can. So things like I can get rid of the parentheses, maybe get common denominators, stuff like that. So like here I can multiply by 5. Remember that you can treat the 5 as like 5 over 1. So the 1 on the bottom, we'll just leave it at 9 on the bottom. On the top, you multiply everything by 5. So you get like 5x plus 25. That's a little bit better. We got rid of the parentheses, but still no x. We could try and maybe combine stuff by getting common denominators. Because here we have a 9 on top and 9 on bottom. We could rewrite 9 as 81 over 9. Remember that 9 squared is 81, 9 times 9 is 81. So this 9 is the same thing as 81 ninths. So we can actually do that. This is just getting common denominators, so we can do some combining. So if I take this minus 81 over 9, now I can combine them because I have matching denominators. So I got 9 on the bottom, I got 5x. 25 minus 81, what is that? Negative 61 plus 5 is negative 56. That's what you get. And we keep working, but eventually at some point we should give up because you'll notice that no matter what we're doing, it's not really getting a closer to x. And this is not working out. This is not equal to x, which tells me already that even though these kind of looked like they might work out, they don't. These are not inverse functions. Then if I stop and look a little closer, you might kind of see some ideas why. Notice here that we're multiplying by 5, and here we're dividing by 9. Well, yes, multiplication and division are opposites, but multiplying by 5 and dividing by 9 are not opposites. Here we're subtracting 9, here we're adding 5. Well, subtraction and addition are opposites, but subtracting 9 and adding 5, those are not opposites. So it's not always good enough just to look at the equations and know. I've had people in the past on the test try and say, okay, well, this is the statement, then the inverse function is going to look like blah, just because it looks the opposite. No, you got to be careful. You got to make sure that it really is the opposite. And the way to check is by doing the composition. If you can simplify down to x, it's opposite. If not, it's not. So these are not inverse functions. They're not inverses. They're not the opposites of each other. They looked a little bit maybe at the beginning, but they weren't. Let's try one more set. Let's see if these ones are inverses. Again, they don't look like they might be, because here we have like subtracting 1, adding with 2, division on both. Like, I'm thinking maybe not. We don't know until we check. So let's check. Let's see what happens. We'll do f of g of x first, which means we're taking this g of x, 2 plus x over x, and that's what's plugging in. So 2 plus x over x, that's what's getting plugged in into our function. So we're replacing this x down here with all that. So we get 2 over 2 plus x over x, all that over x, minus 1. And this one's kind of messy, and this is part of why I put this on here, because I wanted to give you help before you saw this in the homework. This one, to try and simplify it, we do need to get rid of this fraction inside of a fraction. We have fractions with fractions. We call these compound fractions. Not very nice. Trick here is to multiply by this denominator. Because if we multiply by x on this whole part, we can get rid of the denominator on here. And you can do that on a fraction as long as you multiply both the top and the bottom by x. Remember, you can multiply a fraction by anything you want as long as you do it to both the top and the bottom. On the top, that's easy. You just get 2x. On the bottom, this x is going to go to both parts, right? We're going to go to both the first part and the second part. On the first part, we'll be dividing by x and multiplying by x, and they'll cancel. So we just get the 2 plus x because of that canceling this x on the bottom. Then we do negative 1 times x, so we get a minus x because you're taking this x times 1 to get x. Now we can simplify a little bit because we got rid of those fractions. Now we can see that x minus x, those cancel. So we just end up with 2x over 2. And now we have a 2 on top and a 2 on the bottom. So we're multiplying by 2, dividing by 2. Those cancel, and we're just left with plain old x. So that is checking out, right? It works so far. We only checked one direction. You have to check both. This is a common technique. Anytime you have these fractions inside of fractions, you can look at the bottom of that fraction. And if you multiply both the top and the bottom of your big fraction by that denominator, you get rid of the little fraction inside of your big fraction. That's a pretty common technique. So I wanted to show you that. Okay, let's try to do the next one. Let's go backwards. Let's do g of f of x. I'm going to just write it in green so we can see this is different. Going the other way now. So instead of doing the g function first, we're doing the f function on the inside. So it's going to be g of 2 over x minus 1. That's what goes inside. And then g is this guy, 2 plus x over x. And both of these x's get replaced by all this stuff. So whenever you have more than one x, all get replaced by this. Because this is all replacing x. So the g function, we have 2 plus 1. Instead of x, we'll have this whole thing, 2 over x minus 1. And on the bottom, we have 2 over x minus 1. Okay. So now we got this whole thing divided by this whole thing. Now the nice thing here is noting that when we're dividing by fractions, remember there's a trick. When you're dividing by just a single fraction like this, you can flip the bottom and multiply. So we're dividing by a single fraction. Couldn't do it up here because there's a fraction and some other junk. And since we're just dividing by a single fraction, we can flip and multiply. So this becomes 2 plus 2 over x minus 1 times, so this whole thing times, x minus 1 over 2. So that's the trick. If you have divided by a fraction, you can flip and multiply. If you take this to the first one, so we take all this stuff to the first one, there's a 2 on top, 2 on bottom. Those cancel, so you're just left with x minus 1. Right? Because 2 on top, 2 on bottom cancel. Then we go to the next one. So we go to this one here, multiply this one. We'll still have a 2 on top, 2 on bottom. Those cancel. You have an x minus 1, x minus 1 top and bottom. Those cancel. Since everything's canceling, what are you left with? Well, you're actually left with a 1, right? Because you think 2 over 2, that's 1. Anything over itself is 1. So this ends up canceling down to a 1, and it's a positive 1, so we get plus 1. So we get x minus 1 plus 1, but then the minus 1 plus 1 cancels, and we're left just plain x. So that one checks out as well. It worked both directions. It didn't seem like it was going to, but it does. It actually does work. It looks so weird. And that's why you can't just look at an equation and know what the inverse is going to look like. Sometimes they can look very different. These two look so different, but they are inverses. They are opposites. And the way to check them is by doing the composition. Plug one into the other and then go the other way. And either way, you should be able to simplify down to just a plain x. So in this case, yes, f and g are inverses. And again, this means that we can start calling this g function. We can actually call g of x. We can call that f inverse of x. It is the opposite of the f function. There's only one opposite, and this is the opposite. We found it. This is the inverse. It goes backwards. Okay, now, one really cool thing about these inverse functions is they really show up well on graphs. We actually have a test for these. It's pretty straightforward. It's called the horizontal line test. The horizontal line test says that you can, if it's possible to intersect the graph of a function more than once, so if you intersect the graph of a function more than once is the big thing, with a horizontal line. So we're going horizontal, not vertical. So side to side, not up and down. Then it's not a one-to-one function. And remember, if it's not one-to-one, it does not have an inverse function. So that's what this says. The horizontal line test tests to see if it's one-to-one and if it has an inverse function. We had the vertical line test before, right? And the vertical line test just tested if it was a function. So like all these pass the vertical line test. They cross only once they are functions. But the horizontal line test checks to see if it's a one-to-one function. So like here, if I draw a horizontal line anywhere on here, it passes. So yes, this linear function is one-to-one. It has an inverse function. So all those straight line functions, diagonal line functions, those are all inverse functions. They are, they have inverse functions. They are one-to-one. Now here, this is a pretty common parabola. We saw a bunch of these, and this one actually fails, right? Because I can draw a horizontal line right there, crosses twice. So this one does not have an inverse function. Parabolas, these quadratic functions, they don't have nice inverse functions because they do fail. This one fails the horizontal line test. It crosses twice, so it's not one-to-one. It does not have an inverse function. This next one here, this is a cubic function. It also fails, right? Because you could draw a line right here that crosses 1, 2, 3 times. If it crosses anything more than twice, it fails. It's not one-to-one. It does not have an inverse function. Last one, this is also a cubic, but this one you'll notice is nice and smooth. It doesn't bump. So this one actually passes. No matter where you draw, you will not cross more than once. So yes, this one is one-to-one, which means, again, it does have an inverse function. So they have inverse functions if they are one-to-one. And again, I don't really care which way we say it, right? You could say this one is one-to-one, this one has an inverse function. They both mean the same to me because if it's one-to-one, it has an inverse function and vice versa. Now, what do you do if you just get the equation of a function and people ask you about it being one-to-one? The nice thing here is that you can just graph. Because if you look at the graph, you can tell whether it's one-to-one because you can use the horizontal line test. So if anybody ever gives you a function that says, is it one-to-one? If they give you the graph, they give you just the function, well, just graph it. That's why we have a fancy graphing calculator. Here I need to do a cube root, so I'm going to hit the math button. Remember this math button over here is our favorite button, math button, because it has things like the cube root function right there. The cube root x minus 2, so type in that x minus 2, and then you can just graph it and look. So hit the graph button. Is it going to pass the horizontal line test? So look at this and you can see as it goes to the right, it just goes up and up and up and up over to the right, and it will pass the horizontal line test. So yes, this one works out. If I draw a little graph real quick, the function is on there, and it kind of goes over and it goes up and it keeps going. It looks like that, and it passes. No matter where you cross it, it crosses only once. So yes, it's one-to-one. It does have an inverse function. Let's try the next one. You guys probably already have a guess on the next one because you notice that is a quadratic. So hopefully you know what that means. 5x squared plus x minus 1. Graph it. And you can see it is the typical parabola shape. And of course that fails the horizontal line test. So we know right off the bat it's a parabolic that it's not going to have a nice inverse because those horizontal lines will cross more than once. It's not one-to-one. It doesn't have an inverse function. So for this one, let me draw it. I'm going to draw a function that's going to look like this. And it's going to fail, right? I can draw one right here. And that's not going to be a one-to-one. It's not going to be a one-to-one function. It's not going to have an inverse. So this one is not one-to-one. Doesn't have an inverse function. Okay. Next thing. So one thing that's really cool about a function and its inverse. If you graph a function and its inverse on the same graph, they have this cool property where they make a symmetry. So here we have, this is a function. This curve right here is a function, and this is its inverse function. You'll notice that if you graph both this one and this one on the same graph, they're symmetrical over this diagonal line. So you have this, this diagonal line, it's the line y equals x, and they are symmetric over that function, over that line. So the function and its inverse, these two functions, you graph both, will have this symmetry. It has to do with that whole switching the x and y, right? So if I think about the x and the y here, a and b, I switch those b and a, it's going to give me this corresponding point over here that's going to give me that symmetry. So there's going to always be that. So one way to actually graph a function's inverse is to take the function and just switch its x's and y's. So let's do that here. We'll take each one of these points, and we'll switch the x and the y, and we'll get an inverse point, the point on the inverse function. So this is the original function, f of x. Let's look at the inverse. So first off, instead of doing -3, -2, we do -2, -3. That would be our point right here. -2, -3. Instead of -1, 0, we do 0, -1. So that would be that point 0. -1 right there. So at 4, 2, we do 2, 4. That would be a point right here. 2, 4. So if I connect those points, if I connect those up, this one and this one, you can see that this inverse function and this other function, they do make that nice symmetry now. So this is the graph of f inverse of x, this guy in green. And it does have that symmetry, right? If I draw this line right through the middle, it's not perfect because I'm freehanding it, but you get the idea. If we draw this line right through the middle, that line y equals x, then it does make a symmetry over there. Points that were above are below, points that were below are above. So if you graph a function that's an inverse, they always have a symmetry. In fact, this is one way to check a function that's inverse. You could graph them both on your calculator just to see what they look like, what the function and the inverse look like. So that's something you can check. One thing you have to be careful with, your calculator's graph is a little wider than it is tall. So sometimes it's hard to read the symmetry so much because it's like 10 wide and 10 tall, but it's kind of stretched out because it's a wide screen. So sometimes it's hard to see the symmetry, but if you graph a function and it's inverse and there are a function that's inverse, they should show up like this, with the symmetry on there. Okay, so we got the idea. We talked about functions, their inverses, all that stuff. The big thing we want to do, and this is probably the most important in this part of the section, is let's talk about if I give you a function, how do you get the inverse function? What if I don't give you the inverse? Because we did the problems where you already had it, you wanted to check if it was an inverse. The last part is to say, okay, if you have a function, how do you find its inverse? And this is the process. So the very first thing you do is we're going to replace the f of x with y. And that just makes it easier to work with, because remember that f of x and y are the same thing. They're both just the output. We just like to work with y, because if we try to work with equations, it's kind of confusing to work with f of x. So any equation that we start with, we're going to replace this with y, just to make it easy. So we just have x and y. We still know this is a function because that's what the notation's for. It tells us it's a function. But now we can work with it a little bit easier. We're just working with y instead of f of x. Second thing, switch all x's and all y's. So that's probably the most important thing. When it comes to doing this, you need to know you need to switch the x's and y's. Remember, that's how you get the inverse. The inverse function, it has the exact opposite x's and y's. So we take this, we switch it, so it's x equals 3y plus 5. Now it's an inverse function. This is the inverse function. Now the problem is when you do that, you get an inverse function solved for x. And when it comes to graphing and stuff like that, it's not usually what we want. We usually want a function solved for y. So even though this is the inverse function, because we did switch x and y, we're going to have to solve for y. That's going to be your next step, because most people want their functions solved for y or f of x, right? So that's going to be the next thing, solve for y. So to solve this for y, pretty straightforward. We're going to subtract 5 from both sides. So that will get rid of this 5 here. So we get x minus 5 equals 3y. We need to get rid of this multiplication, so we'll divide both sides by 3. So undoing that multiplication, so we can cancel that 3 out. We have to divide both sides. It doesn't have to look a certain way, so you have to worry about dividing both parts by 3 or getting things to look a certain way. You really just want to get y by itself. So this is what I did. Now I got y by itself. I'm going to put it on the left here. Put y on the left, and then the x minus 5 over 3 on the right. And that's just a preference thing. You can leave the y on the other side. It's not a big deal. Because the equal side, remember, the sides don't matter. You can swap sides on equals, because it just says the two sides match. Okay, now I got y by itself. Last thing, we got to go back and say, okay, now that we have the inverse function solved for y, let's label it. So we're going to label this f inverse, because that's what it is. It's the inverse function. So we're going to rewrite this as f inverse of x, so that everybody knows that x minus 5 over 3 is the inverse of that function we started with. And if you look at it, it makes sense, right? What's the opposite of adding 5? Subtracting 5. Well, What's the opposite of multiplying by 3? Dividing by 3. Now, I do have students, like I said before, they'll try and look at this equation and they'll just try and write this equation because they can say, oh, I know what the opposite of adding 5 and dividing and multiplying 3 is. But it's so easy to do something that's close to this that's not quite right. Because what if you just put x over 3 and then put minus 5 on the side? It'd be wrong. It wouldn't be the same expression. So this process is the process you have to do. You have to take it, write it with y, switch the x and y, solve for y, and then label it as an inverse function. So that's the answer. That is the inverse function. Now, if you want to check these, how you check them? Well, you check by composing. You do the f and f inverse, and you compose them back and see if you get x both ways. So I'd take this expression and plug it in here for x. I'd simplify it down. Take 3x plus 5, I'd plug it in for x, and simplify it down. Either way you do it, you would get, x both ways. Remember that if you get x both ways, they are inverses, and you've done it right. I'm not going to make you check these, but if you want to check them, that's one way to check them. The other way to check these would be to graph them both. So if you want to, you could graph them both and see if they work that way. Let's try that real quick. Let's plug both of these in. So I'm going to do y equals 3x plus 5. So that's the original one we started with. And then parentheses x minus 5 divided by 3. Because we want everything on the top divided by 3. So that's why I had to put parentheses around the top. They are inverses, so when we graph these, you should make that symmetry. So you can see the first one looks like that, and the second one looks like that. And you think at first, is that symmetric? And then you kind of look at the diagonal line, you see that, yeah, if you draw a diagonal line right here through the middle, it would be symmetric. It's a little harder to see on the graph, like I said, because of it whole being kind of stretched out. One thing you could do to fix this a little bit, oh, mine's actually not zoom standard. Usually my zoom is 6 zoom standard, and so it probably usually would look like this. And that might look even worse, harder to read. I guess my graph I'd already zoomed in for something else. But a lot of times what I'll do is I'll take the window dimensions in. I'll make this like 15 wide and 15, 15 left and right. Because 15 by 10 kind of fits that screen a little bit better than 10 by 10. Because 10 is, should be about, this high. But if you make it this way, it's kind of wide. So you can see that actually shows a little bit better than if it was 10 by 10. If that didn't make a lot of sense, again, you could check these by doing the composition. But the idea is that you should be able to draw the line y equals x. So draw the line y equals x. It should go right through the middle of the two and split them right down the middle. You can see it does, right? It splits them right down the middle. It goes right through that point where they cross. Stuff is always spaced out evenly on both sides. So you can see that, yes, these are symmetrical. So they are symmetrical if you graph. So I should just put a note here, or graph to check for symmetry. Again, you have to graph both equations. If you graph both equations, they should have that symmetry over y equals x, which is that diagonal line. That's what the symmetry we're looking for. Okay, let's do a couple more finding the inverses, and that's all there is to this section. You should be able to find those one-to-one functions, figure out if they're one-to-one, and then you need to be able to find inverse functions. Okay, so we're starting off this one. We have the equation 5x squared minus 2. Wait a second. You see that, and hopefully the red flag right there, right? Because we said already the quadratics don't work, right? We know that if we graph this, quadratic 5x squared minus 2, it's going to be a quadratic. It's going to, I think it crosses about down here. It's going to look something like this. And that would fail the horizontal line test, right? Because horizontal line test would cross twice. So it's not one-to-one. But you'll notice there's a second part here. You'll notice that they say we're only using this function when x is less than 0. And sometimes that's what they will do. If you want a function that's one-to-one, a function that does have an inverse function, what you do sometimes is you just, instead of using the whole function, you use just part of it. And so this one just says just use the left side. This part where you're going from 0 to the left, this is the x is less than 0 piece. We don't want this piece because here x is greater than 0. So we're not using the whole function, we're just using this piece. And so by just using the left piece, well, if you ignore the right, then yes, that is one-to-one because it does pass the horizontal line test if you take off the right piece. So this function, even though it starts off as a parabola, and you're like, wait a second, parabolas aren't one-to-one. Well, we're only using half the parabola. So you'll see that sometimes. If they'll give you a function, they'll say, oh yeah, it's one-to-one because we only used part of it. Here's the restriction. X has to be smaller than 0. We're just using the left half of the parabola, not the whole thing. That's why we're allowed to use it. Okay, so now we can go ahead and do this. We do have to be a little careful about our answers, so we'll talk about that at the end. Let's go ahead and do the same process we did last time, because mostly that's going to be the same. First thing we're going to do is going to write this as y equals, right? We don't like to write with f of x because it's confusing, so let's put this y equals. So we get y equals 5x squared minus 2. Make it a little bit easier. And then once we have it written with y, we're going to switch x and y. So we switch them, so we get x equals 5y squared minus 2. And then once we get that switched, we're going to go back and try and solve for y. So we've got to solve this for y. Now this is one of those quadratic equations, and you could use things like the formula and stuff like that. But this one, because there's no y, there's just a y squared, probably the easiest way to use this one and to solve this one is to use the square root property. So we're going to square root both sides to solve this. But first, we're going to get the y squared by itself. So that when you square root, the square and the square root cancel. So we're going to isolate this y squared. So to do that, we're going to add 2 to both sides. So we're getting rid of this minus 2. So we get x plus 2 equals 5y squared. Now we want to get rid of this multiplication by 5, so we're going to divide by 5. We have to do that to both sides. Get rid of that 5. Let's get x plus 2 over 5, the whole thing over 5, equals y squared. Then we can take that, and square root both sides. So we're going to square root this side, square root that side, square root of both sides. And so we get y equals square root of x plus 2 over 5. But hopefully you remembered, when you use the square root property and square root both sides, you cannot forget to put in your plus or minus. So when we did this step, we should have actually put a plus or minus here. And this is where we'll use this x less than 0 to figure out something. We know we can't have 2 different answers for our function, right? We can't have both the positive answer and the minus answer. So we've got to figure out which one we're actually going to use. Well, since x is less than 0, that is the domain of f. That's the inputs, right? To go backwards, to have the inverse function, we know that the range of f inverse, the inverse function, the y values for the inverse have to be the same values. Remember, we said with the definition of these functions, these inverse functions, we had this, back a few pages, let me scroll it up there for you again. We said that the domain of your function is the range of your inverse, because they go backwards, they're going opposite of each other. So the input of one is the output of the other. So that tells us that the inputs, the domains, the x values for this one are negatives, then the range of the inverse function, the results for the inverse function, all have to be negatives. So we're not going to use the pluses, we're just going to use the minuses. If you think about it, if you take this part of the function and you flip it over this diagonal line, you'd see how you, instead of getting the numbers up here, you get the numbers down here, which would be negatives. Everything would be negative. So that's what's going to happen when you flip it like this. You're going to make it all negatives. So we want the negative values for this. So that's how we know to use the negative and not the positive. That's again, because the domain here, we know about the range for the output. Last thing we're going to do is you have to rewrite this as an inverse, because we always want to have the proper notation. So this is f inverse of x, saying that's a function that's the opposite of that function. And the inverse function is negative square root of x plus 2 over 5. That is the inverse function. Kind of a weird one. I probably wouldn't do this to you on the test, so don't freak out too much about it. I do think you see it in the homework, and that's why I want to make sure I talked about it. And talk about this, the fact that you can restrict the domain to make a function work, because that's the important thing to know, is that we don't always work with the whole function. Sometimes we just work with part of it. But on the test, I'll probably give you one where you don't have to worry about the restricting the domain. Okay, let's try one more. One that doesn't restrict domain, so we'll do one more before we call it quits. Okay, so we have function 7 over x minus 4. They want us to tell if it's 1 to 1, so we can actually check that. Again, remember the way to check that is just to graph it. So if you want to, you can just go back in here and graph this to make sure that it does have an inverse. So 7 divided by, make sure when you have a fraction like this, you type it in with parentheses around the bottom, because you want the x minus 4 see what happens first by order of operations, right? You always do the subtraction on the bottom before you divide. So that's the parentheses there. Otherwise the calculator doesn't know what's going on. And you can see that it just goes like that, and it goes like this, and no matter where you draw your horizontal line, you don't cross more than once. So yes, it is 1 to 1. So we could check that first. I checked it is. The graph looks like this, with the line here, something like that. Oh, I guess I'm a little bit off, but well, you get the idea. You saw what the graph looks like. It looks like that. So it is 1 to 1. So since 1 to 1, we can go ahead and do this. We're going to rewrite this as instead of f of x as y equals 7 over x minus 4. So we rewrote it, and then after we rewrite it, we're going to switch x and y. That's the big step, right? You would just want to get a y in there so we have something to switch. So switch x and y. This becomes x equals 7 over y minus 4. Okay, so we switched x and y. Now we need to solve for y. A few different ways to do this, but I think the easiest way is to go back to the way we talked about when we were working with these rational equations. Just multiply by the denominator. If you have a common denominator, remember you can always get rid of the fractions by doing that. So I'm just going to multiply both sides by y minus 4, because that will get rid of my common denominator. So if I multiply y minus 4 on this side, they cancel, so you just get 7, because the bottom and the top here cancel. And then I'm also going to, after multiplying this time, I'm also going to multiply that side. So I have to multiply it to both sides. So we get x times y minus 4 on that side. So we got rid of the fraction just by multiplying by the LCD. So this is just our way to kind of try and solve for y. We can't really solve for y when it's on the bottom of the equation. That's why I had to do this, because I really want to get y on the top of the equation, not on the bottom of the fraction. So we multiplied by the LCD just to get rid of the fractions, so we don't have to worry about y being the bottom. Now here, I'm going to go ahead and just get rid of this x because I want to get y by itself. So let's go ahead and undo this multiplication by dividing. So that's one way to get rid of that x, right? Just to undo is to divide. So we get y minus 4 equals 7 over x. Last thing, I want to get rid of this minus 4, so I'm going to add 4. So that's the opposite. So I'm going to add 4 to both sides to undo the subtraction. We get y equals 7 over x plus 4. This should be the inverse, so I can go ahead and label it as f inverse. F inverse of x equals 7 over x plus 4. That's my inverse function. If I want to double check it, I graph them both. Remember, if you graph both the functions, they should make that nice symmetry. So let's try this. Let's see what it looks like. 7 over x, and then add 4. And let's see if it does give us the symmetry we're looking for. And it's hard to tell sometimes. Sometimes, like I said, I think it's easier to put that y equals x line in there and then see if it's symmetrical. And you can see how it does cross right at those points where they intersect. That's a good sign, because then you can see if you look across this line, they are symmetrical across the line. Like they're always crisscross, opposite across that. So yeah, I'd say yes, this is symmetrical. So yeah, this is an inverse function. We found the right inverse. We checked it out, found it. Okay, one last page, and then we're done with this section. This one, I thought I looked through all my notes. Okay, I don't remember this for some reason, but we'll go ahead and do it. So this one, we're finding the 1, 1 function of this function. This is going to be another one we have to worry about the domain on here. So let's look at that while we do this. So starting off, we're going to do square root of x minus 2 as our original function. It is a 1-to-1 function. If you're not sure, you could go back and graph it, but they do tell us it's 1-to-1. To find the inverse, we're going to switch, x and y like always. So first I'm going to write it as y equals square root of x minus 2, and then we'll switch x and y, so we get x equals square root of y minus 2. Okay, so we can get that like that. Now the next thing we want to do is to get rid of this, to get y by itself, we have to get rid of this minus 2. So we're going to add 2 to both sides. So we're working on getting that y by itself, because you always want to solve for y to get the inverse. So we get x plus 2 equals square root of y. And now to get rid of the square root, we can just square both sides. We're going to take this side and this side. We're going to square them both. So we can square that. Square and square root cancel. So we get x plus 2 quantity squared equals y. And now when we solve for y, we can take this function. We can say, okay, this is our inverse, so we'll call this f inverse of x equals x plus 2, the quantity squared. However, if you're paying attention, again, this is actually a quadratic, right? If you take this x plus 2 and you square it out, I think you end up with like x squared plus 4x plus 4. You can factor if you want to FOIL that out, which is a quadratic. And quadratics, we know, aren't one-to-one. They don't have inverses, which means that this one we actually do have to restrict the domain. We have to work with what the domain is so we don't have the whole function. So we have to look at x and say x is either bigger than the number or smaller than the number. We have to think about what that is. Well, thankfully, we can figure that out by looking at the original function. So first off, before you get too much further, let's talk about the original function. This guy right here, what's he look like? Well, remember, square root of x functions start at 0 and go up to the right. And they kind of like level off. That's what a square root of x function looks like. But this one has a minus 2. Your graph transformations tell us that minus 2 shifts it down 2. So instead of starting at 0, it's going to start here at negative 2. It's going to go up to the right. Usually we would be able to square root 1 and get 1, but that shift down 2 would actually move it down here to the point right here. Square root of 4 usually gives us 2, but shift down would give us 0 right there. Square root of 4 would be 2, minus 2 would be 0. So it actually would look like this. That's what our original function, that's f of x. So you can see with f of x that it only has values for x's greater than 0. So x has to be greater than 0 for this guy, for the x range, for this function. And its domain, I guess I can just put down here, domain is from 0 to infinity, bracket for the 0 because we actually reach 0. And its range, its up and down range, is from negative 2 up to infinity, right? Because it starts at negative 2 and goes upwards. It doesn't ever level out, so it's always going upwards. So its range is from negative 2 to infinity. Well, because of knowing that information about the original function, remember that we can just switch x and y and find out stuff about the inverse function. So the inverse function, its domain is going to be negative 2 to infinity, because it's got to have the range of the other one as its domain, so they're opposite. And its range is going to be 0 to infinity. Its range is going to be 0 to infinity. So for this one, we can say it's this quadratic function, but it only works when x's are negative 2 and bigger. So it's this. So x has to be greater than or equal to negative 2. So it's this function, x plus 2 squared. You could FOIL that out if you want to have the other answer. I don't care. As long as you get y by itself, I don't really care what this looks like. You can see that is the inverse function as long as x is greater than or equal to negative 2. If I wanted to check this, to put on the graph, I would just graph this. I could plot some points if I need to. Like I put negative 2 in here. Negative 2 plus 2 is 0. 0 squared is 0. So negative 2 you get 0. Negative 1 in here. Negative 1 plus 2 is 1. 1 squared is 1. So negative 1 you get 1. I think the other one's going to be like 0. 0 plus 2 is 2. 2 squared is 4. So on 0 you get 4. And so you get points like this, which makes sense if you look at these points and say, oh yeah, you could take negative 2, 0 and turn it into 0, negative 2. 1, negative 1 turns into negative 1, 1 if you switch the x and the y. 4, 0 becomes 0, 4. So these are just those corresponding points. And you can see that they do make that nice symmetry. If you look down the x-axis, or not the x-axis, the y equals x line, there's that nice symmetry where they are equally spaced. But again, we had to think about the restriction for the domain. So this is the function, but it's only for x's from negative 2 to infinity. If I drew the whole parabola and drew all the pieces over here, then it wouldn't really be the inverse of this function anymore. This function stops here, so this one has to stop here as well. Okay, again, I'm not going to throw a lot of this kind of stuff at you on the test where the domain has to be restricted. I think it's a little bit beyond what we want to do on the test. We should be able to do like this main part where I give you a function, you should be able to switch x and y and solve for y. That's what I'm really looking for. All these last 4 problems, you saw that we'd switch x and y and then we solve for y. And that's the main thing we should be ready to do on these is switch your x and y and solve for y. That's what I really want you to be ready for. Okay, that's it for outcome 1 for Unit 3. So it's all about one-to-one functions and those inverse functions. One of the big reasons we talked about inverse functions is over the next couple sections, we're going to introduce exponential functions. They're the functions that describe how things grow exponentially. Things like bunny populations, virus populations, human population, all these things grow exponentially. Um, and then we're going to talk about their inverses. What is the opposite of that? And so we wanted to introduce the one-to-one and inverse functions now, so that as we get into these exponential functions and their inverses, we can talk about what those look like, and we can think about inverse functions, how functions can be opposites and undo one another, do the opposite of each other. Okay, that's it for this section. I'll see you on the next set.